Assalamualaikum and good evening everyone. We are from the group 4 and this is our presentation for MEB4333, Asset Reliability, Availability and Maintainability. So for our project focuses on RAM study of a natural gas processing plant using Weibull++ and BlockSim. Without further delay, let's begin. Raw natural gas is not clean. It contains impurities like hydrogen sulfide, carbon dioxide and water vapor. This must be removed to ensure the gas is safe, efficient and meet pipeline quality standards. To achieve that, the gas goes through the key processing stages including separations, compression, acid gas removal, dehydration and NGL recovery. So the plant we're studying handles 100 million standard cubic feet per day with 50-50 split between the medium and high pressure gas stream. That concludes the background. Moving on to the next part.
Unplanned downtime in gas processing plants can cause serious issues including safety risks, financial losses and reduced production. Over the last 5 years, key equipment like compressors, suppressors, and pumps in this plant have frequently failed. This points to the presence of high failure rate equipment, also known as bad actors. The core issue is that without a structured reliability, availability, and maintainability, or RAM, analysis, it becomes difficult to identify these recurring failures and take action. This limits the plant availability to maintain consistent performance and reach its target of 99% availability. That brings us to the main objective of this project, which is to conduct a RAM assessment to improve plant reliability. Specifically, we aim to define key assumptions and parameters used in the RAM analysis, calculate average pump availability using 5 years of failure and repair data, identify which equipment is contributing to the most downtime, and finally develop strategies to improve availability and achieve the 99% target. This structured approach will help the plant to make informed decisions to reduce failures and improve performance. This slide presents the failure and repair time data used for our RAM analysis. It includes major equipment from the gas processing plant, such as compressors, pump, drums, and heat exchangers. To analyze the data, we use Weibull++ software, specifically the distribution wizard, to determine the most appropriate distribution model for each equipment's failure and repair behavior. This tool evaluates multiple distributions and select the best fit based on statistical tests and goodness of fit criteria. On the left table, we showed the failure time data where different distributions such as normal, exponential, and log normal were selected depending on the equipment's failure trend. Corresponding parameters like mean time, standard deviation, eta, or beta are listed based on the selected model. The right table shows the repair time data where most equipment followed exponential 1p or log normal distributions, each with parameters like mean time, log mean, or log standard deviation. These fitted distributions and parameters serve as essential inputs for the next step of our RAM simulation and availability calculation.
Next, I am going to talk about the reliability modeling approach used in this project, specifically the use of the reliability block diagram or RBD. The RBD is used to model the configuration and reliability behavior of a natural gas processing plant. Instead of showing the physical layout, the RBD represents the logical sequence of operations, which allow us to simulate how different components interact and how individual failures can impact the overall system. This makes it especially useful for performing structure simulation and understanding reliability and availability across the plant. The plant we are modeling processes 100 million standard cubic feet per day of raw natural gas. This gas is split evenly into two streams. One is medium pressure or MP and the other is high pressure or HP. Both streams go through key processing units such as separation, compression, acid gas removal, dehydration and NGL recovery. After passing through these units, the treated gas is sent to the sales pipeline. To make the model realistic yet manageable, we applied several assumptions. First, we only included equipment that directly affect production throughput. This means that support systems like valve, control system, and utilities were excluded to keep the model clear and focused. Second, units that don't have a significant impact on production, such as condensate treatment, sulfur recovery, and tail gas treatment, were modeled as non-failing procs. Third, we use redundancy logic where applicable. For example, backup pumps and alternate flow paths were modeled using parallel or 2 out of n logic, which reflects how this system works in real life. Finally, we applied standby logic to systems that alternate between active and standby modes, such as the molecular sieve beds in the dehydration units and the turbo expander system, which is backed up by a JT valve. This assumption helped us to create a model that is both technically valid and suitable for RAM analysis using BlockSim. Now, I will briefly explain how each major unit is modeled within the RBD. For the MP and HP separation units, both streams go through 3-phase separators. After that, the MP gas is compressed and then mixed with the HP stream. The combined gas then enters the feed gas compression units, where a steam turbine-driven compressor boosts the pressure. The gas is cooled before moving on to acid gas removal. Next, in the acid gas removal unit, hydrogen sulfide is removed from the gas using amine adsorption. This resulting rich amine is directed to the regeneration unit. In the regeneration unit and sulfur recovery units, we model system redundancy using parallel and 2 out of 2 logic to reflect the presence of critical pumps. Next, in the dehydration unit, we model molecular sieve beds with standby logic. When the active beds require regeneration, the standby bed takes over. Similarly, in the NGL recovery unit, we included the turbo expander system along with a jetty valve as a standby component. Only the active blocks is considered to influence availability. Finally, in the residue gas compression units, dry gas is sent to the sales pipeline. This part of the system includes a monitoring block which is modeled as a non-failing. The complete reliability block diagram ties all these units together and gives us a full picture of the plant's reliability behavior. This model serves as the foundation for simulation and RAM analysis, allowing us to evaluate overall plant availability and identify any critical equipment that may prevent the plant from reaching the target of 99% availability. That concludes the overview of the modeling approach. In the next session, we will go into the simulation result and look at how critical components are identified based on their impacts on system availability.
On this slide, we present the core result of our plant availability analysis. To ensure the accuracy of our finding, we use 2 different models, a software simulation and a manual calculation. First, looking at the left side of the slide, you can see the result from our simulation using the Weibull++ software. We model the plant as a series system, which you can see in the RBD. The simulation calculated a system availability of 78.99%. Next, to validate this result, we perform a manual calculation shown on the right. Here, we calculated the inherent availability for each individual component and then multiplied them together. This manual method gave us a result of 77.65%. As you can see, the result from both methods are very close, which confirms our finding. The minor difference is about 1.3% as expected, as the simulation software can account for the full statistical distribution, while the manual calculation relies on the mean values. The key takeaway is that both methods points to the same conclusion. The plant availability is critically low. For our analysis, we will use the more conservative figure of 77.65%. This means over a 5-year period, we can expect a total downtime of approximately 480 days.
So now, I'll be representing the downtime criticality index, which shows how much each equipment contributes to the overall system downtime. Based on our analysis, the turbine clearly stands out as the most critical equipment due to high failure frequency. They are followed by the demetanizer, which also shows significant downtime impact mainly because of its longer repair durations. Other equipment such as the slide catcher, discharge drum and separators fall into the medium criticality group, where both failure rate and MTTR are moderate. Meanwhile, assets like compressor, pumps, motor and filters are categorized as low criticality. Their impact on system downtime is minimal and less urgent. So this finding will help us identify which components should be prioritized in our maintenance and improvement strategies to reduce overall downtime.
The 2 main recommendations to boost availability are to focus maintenance and upgrades on critical equipment. By using the Downtime Criticality Index (DTCI), we prioritize bad actor equipment such as turbines and the demetanizer. Concentrating resources here maximize the impact on overall downtime reduction. The second one is to implement redundancy and reduce repair time (MTTR). We recommend installing standby units for critical equipment and continuously enhancing repair efficiency through better tooling, skilled personnel, and streamlined spare parts management. Following this recommendation, the improvements were introduced iteratively as shown in the table. Without improvement, the turbines alone accounted for about 73% of downtime, with the plant's availability at a very low 5.1%. For the first improvement, added one standby unit for each of the turbine discharge drum separators and others, raising availability to 22.5%. For the second and third improvement, further redundancy added to the reflex and suction drums, and MTTR was improved for turbines and compressor, gradually increasing availability to over 42%. For the fourth to sixth improvement, focus on lower criticality equipment, pumps, absorber, motors, and filters by adding standby units and optimizing repair times, culminating in a final availability of 97%. This stepwise approach allowed us to systematically address the highest impact areas first and then refine improvements on less critical equipment. In this slide, we see the updated reliability block diagram (RBD) of the natural gas processing plant after the series of improvements. The RBD visually presents how the equipment redundancy and standby units were integrated into the plant architecture. The main system RBD shows key units grouped into subsystems such as MP and HP separation unit, feed gas compression, acid gas removal, amine regeneration, dehydration, and NGL recovery. Critical components like turbines, compressor, pumps, and separators include standby units configured in parallel blocks, increasing system reliability. Standby units and improved maintainability are modeled with parallel and standby logic to better stimulate real operational behavior post-improvements. This RBD enhancement reflects how our iterative improvements physically and logically translate into higher system availability by minimizing bottlenecks and single points of failure. To conclude, our detailed RAM study identified turbines and the methanizer as the primary bad actors causing most downtime, with a baseline plant availability of just 5.1%. Using the TCI analysis, we prioritize equipment for improvement and apply a phased strategy of adding standby units and reducing MTTR. These iterative improvements successfully increased availability stepwise to 97%, demonstrating the effectiveness of combining redundancy with maintainability upgrades. While reaching above 97% availability is challenging and costly, focused efforts on critical assets yield the highest returns. For sustaining and further improving availability, maintenance and monitoring should focus continuously on high DTCI equipment to ensure priorities remain aligned with evolving operating conditions. Implementing reliability-centered maintenance (RCM) practices is essential to proactively prevent failures. Additional standby units should be installed strategically, balancing cost with reliability benefit. Continuous technician training and better spare parts management will further reduce MTTR. Regular reassessment and simulation updates are needed to adjust strategies over time. Finally, a cost-benefit approach is crucial when considering further redundancy or advanced predictive technologies to inch closer to the 99% availability target. Following this recommendation will help maintain world-class plant reliability and operational excellence.